Right now, you probably feel like you're sitting still. You feel a familiar, invisible weight pressing you down into your chair. For 3 centuries, we've called this force gravity. But that downward pull you're feeling right now, it isn't a pull at all. Isaac Newton's foundational force does not actually exist. In 1907, Albert Einstein had a realization he would later call the happiest thought of his life. He imagined a man falling from the roof of a house. While the man is falling, he doesn't feel his own weight. If he were to let go of an apple on the way down, it wouldn't drop to his feet. It would simply hover there, perfectly stationary relative to his body, as they both plummet toward the ground. This animated diagram compares 2 digital accelerometers. If you look at the one strapped to the falling man's chest, it registers exactly 0 acceleration. The reading of 9.81 meters per second squared only shows up on the device sitting stationary on the ground below him. The numbers reveal a strange truth. A falling person is not accelerating at all. They are coasting. In the universe's physics, freefall is the default state of true rest. To see why that matters, we can move the thought experiment off the Earth completely. Picture a windowless elevator drifting in deep space, millions of miles away from the nearest star. Look at this technical cross-section comparing an elevator falling on Earth with one drifting in deep space. In both environments, a passenger floats weightlessly. The physics are mathematically identical. Freefall feels exactly like floating in empty space. Now, if that deep space elevator fires its engines, accelerating upward at 9.8 meters per second squared, the floor rushes up to catch them. Inside that windowless accelerating box, the passenger's knees feel a sudden downward pressure. It feels exactly like standing still in a normal room on Earth. Since that upward rocket thrust flawlessly mimics the feeling of gravity, Einstein drew a radical conclusion. Feeling weight on Earth means you are in a state of constant acceleration right now. Standing still takes active physical effort. This raises an immediate logical question. If gravity isn't pulling on falling objects, why do they curve downward toward the planet instead of flying straight off into space? The answer requires us to look at geometry. In this wireframe model, 2 travelers start 1,000 kilometers apart on the equator. We tell them both to walk strictly due north. Eventually, they will collide at the North Pole. There was no invisible magnet pulling them together. If we flatten the globe into a 2D plane, we can see they walked in perfectly straight lines. The convergence was dictated entirely by the curvature of the surface beneath them. In physics, these straight paths across curved geometry are called geodesics. Our universe expands this concept into the 4 dimensions of space and time. Massive objects, like planets, warp this geometry around themselves. Falling objects are merely coasting along their straightest possible geodesics through that warped space. You can see this principle at work with the weightless astronauts aboard the International Space Station. They are traveling in a perfectly straight line through 4-dimensional spacetime. It is the Earth's massive bulk that warps their straight line into the helix we observe as an orbit. Orbits and falling arcs do not require an invisible tractor beam. As the physicist John Wheeler summarized, matter tells spacetime how to curve, and spacetime tells matter how to move. Bringing this abstract geometry back down to your physical body changes how we must define your current state of motion. Right now, the floor beneath your chair is actively blocking you from following your natural geodesic path into freefall. Because you are prevented from coasting freely, the ground exerts a constant physical normal force upward against your shoes. We can prove this mathematically with the space-time geodesic equation shown here. To keep your spatial movement at 0 on Earth, you must factor in this highlighted curvature variable, known as the Christoffel symbol. Because spacetime around Earth is heavily curved, maintaining a stationary position mathematically requires a non-zero proper acceleration. Staying stationary on the surface of our planet demands a constant physical upward acceleration. What you call gravity is the continuous resistance of the ground, pushing you away from your natural trajectory. A geometric theory requires empirical proof. Einstein knew that if his model was correct, the warped spacetime around a massive star should deflect the path of something completely massless, like a beam of light. In 1919, the astronomer Arthur Eddington led an expedition to test this by observing a total solar eclipse. He wanted to photograph starlight passing close to the sun to see if the sun's curved spacetime altered the light's trajectory. During the eclipse, the obscured sun allowed Eddington to see the stars positioned right at its edge. Their positions had visibly shifted, matching Einstein's geometric predictions perfectly and proving the Newtonian model of an attractive force wrong. Today, that same geometric curvature affects how we measure time. Because staying stationary in a gravity well requires continuous acceleration, clocks on Earth tick at a different rate than clocks in orbit. Engineers have to program relativistic corrections into GPS satellites. Otherwise, your phone's navigation would fail by 10 kilometers every single day. The universe operates on geometry, not invisible tethers. Every dropped apple and orbiting moon is simply coasting through the natural shape of reality. That means the downward pull you feel right now, your very sense of weight, is the ultimate physical illusion.